can start then. Okay, then great. Hi everyone. Today, at least on my side, I would be presenting mostly on the ARC-AGI benchmark. So this ARC essentially stands for Abstraction and Reasoning Corpus. So it is a data set which was created by Francois Chollet in 2019. Francois Chollet, for those who don't know, is the creator of Keras. But previously, he worked as a senior software engineer in Google, and he essentially created ARC-AGI in order to assess the reasoning capabilities of deep learning models, or essentially LLMs. And partly, I would also cover as to why the current frontier models kind of have very limited reasoning capabilities, and consequently why they have pretty much very poor performance on the ARC-AGI benchmark. Before I move into this, however, I think it would be better if we can kind of cover a little background on why ARC-AGI was created in the first place. So, as many of you may know, that GPT-5 was released recently, and OpenAI CEO Sam Altman claims that GPT-5 has now attained PhD level performance across all domains. But in reality is when you try to use these models and do a very mundane task or very simple task such as multiplication, you would see that these so-called state-of-the-art PhD level LLMs they are unable to perform basic multiplication. And so if you see on the right here, this is one of my own examples while I was performing research for this presentation, where I give it a multiplication of six-digit integers, basically six-digit floating numbers, and the result is quite close. However, in math, it doesn't really matter if the answer is close. It's more important that we receive the correct answer, because like these kind of questions, they are more deterministic. It doesn't matter if it is close. But it is interesting to see that the answer was close, and we'll kind of discuss as to why this is the case. So obviously now the question is, why is it that these LLMs do so good in these PhD level tasks and perform so poorly in simple mathematics problems? Here, I think it's important to understand the differences between skill and intelligence. So skill is essentially the output that you get after you use your intelligence in order to understand a particular task. So say I work on geometry problems. I understand the underlying concepts of geometry, say about circles. And if I am given any question on, let's say, how to find area of a circle, I know that the formula for that is pi r square, and I kind of understand the deterministic formula of how the area of a circle is calculated. And given the radius, I can compute it. But the way, if you really think about it, how LLMs kind of learn this is they don't really know the formula. I mean, they do, but the way LLM kind of compute the area or any other complex task is through training data, right? So they have seen millions of such examples before, and it is very difficult, at least in complex cases, to kind of understand whether the LLM has actually understood the core knowledge that is required to solve the problem, or is it just that it is kind of an extrapolation of what it has seen on its training set. So this is a very important distinction. So that's what skill is. Skill is I have received some core knowledge on a particular subject, and I try to apply it to arrive at an answer. Intelligence, on the other hand, is a completely different topic. So intelligence, as you'll see on the next slides, intelligence is the process of obtaining a particular skill. So the kind of assumption is that these LLMs are able to solve these highly complex PhD problems. It's because they are seeing these problems before on their training data, and all they're performing is next token prediction, and they're able to come really close into solving these particular problems. But when it comes to something like multiplication, you would obviously not see multiplication between any two random numbers on the internet, right? And that's the basic assumption as to why LLMs don't really do good in tasks like these. So on the third point, which is essentially the third point in this slide over here, that you don't really need you don't need to train your LLM on millions and billions of data to just solve basic arithmetic. All you need to do is somehow embed the core knowledge of how multiplication essentially works. Now, coming to intelligence, right? So there are basically two trains of thoughts that the two main trains of thoughts that people talk about. The first one is the Minsky train of thought, school of thought, sorry, which is essentially it basically defines intelligence, where we essentially say if a machine performs a particular task, which is typically done by humans, that's in a way some form of machine intelligence. And this is more aligned with the skill type of intelligence that I mentioned in the previous slide. And the other one is the McCarthy school of thought, which defines intelligence as the ability of our models to adapt to novelty. And you will see that in this definition, there's clearly a difference between skill and fluid intelligence over here. So here it's not enough that the LLM is able to solve the particular problem. It is also important that it solves the problem it has never seen before in the training data. And I think that's where the major distinction between kind of the broader terms of AI and AGI come in. Because if you keep scaling up your models and you train it on like hundreds and millions of data, I think the LLMs will eventually learn the required priors to solve the examples. But the efficiency is in question here. Is like, how many examples do I actually have to feed my model in order for it to completely understand what it needs to do to solve a problem it has never seen before? And with that, I think I can probably cover system one and system two thinking. So they are essentially, at least many of the neurologists say that typically we as humans think in two different kind of systems. The first one is the system one kind of our brain, which is essentially, I think they also call this as the right side of the brain. So this is more based on intuition. So say I, as a human, perform facial recognition, and I don't need to really think on to understand who my friend is. Like, I can just see it and I can understand inherently that, oh yeah, these are the features and that's essentially my friend. So the system one is essentially mostly based on pattern matching. It is fast, and this kind of aligns with the Minsky school of intelligence that we seen earlier, which is essentially more aligned towards automation, right? And if you look at how our current state of the art LLMs do, not only LLMs, but like any deep learning models for that matter, they actually do extremely well. So if you look at any architecture, facial recognition, I think LLMs, not only LLMs, but like any deep learning models, they currently perform really well. Have system two, which is more on the left hemisphere of the brain. And this is more slow. It is more on the reasoning aspect. It's more deliberate and it's more logical. And this aligns more with the McCarthy school of thought, where, say, again, as a human, I am given a novel task which I've never seen before, right? So it obviously, you do require some sort of reasoning because this task is going to be more difficult and because we have never seen that before, right? So this is more slow and deliberate. And currently, the performance of LLMs is actually very limited. And in order to kind of assess how these LLMs perform in tasks like these, Francois Chollet created the ARC-AGI benchmark. Now, if you look at the presentation over here, you would see, so this is one of the examples that I took from the ARC-AGI website. So the ARC-AGI, every single task in ARC-AGI is essentially an input-output pair where you have a sort of a puzzle. So for instance, in this example, we have these L-shaped blue squares or L-shaped kind of objects. And the objective, as you can see, is to fill out the color of the L shape with a kind of a dark blue color. And you're essentially also given a test input output pair, and your objective is to kind of figure out what would be the correct output pair. And so you would see that these kind of examples, the LLMs would probably have never seen before. And this is kind of a litmus test for the models to kind of check if the models can actually adapt to novelty. And subsequently, the first ARC competition was hosted on Kaggle in 2020. And since obviously Kaggle's resources are limited, I think we only receive like a GPU T4 times 2. So in order to, so obviously there's two competitions. There's one on Kaggle, which is kind of bottlenecked on GPU. So that's more of a test of efficiency. And there's also one on the main website where even offline models trained on any GPU resources, they kind of get a pass on it. Now, before I move forward, I'll just pause for a minute to ask if there are any questions.
Any questions in the room?
Does the benchmark test math, or in this case, it's different than math or numbers? It's like pattern matching.
So every single example is just a puzzle. So in the case I've shown over here, it's just these blocks, and this is just color filling of these blocks in the empty squares over here. And you have different such puzzles where each puzzle's underlying concept is different. So there's a puzzle where we have a concept of gravity, where these blocks, I don't know if you guys can see my mouse, but these blocks over here, they essentially kind of think of them as just falling in this input output grid. So that's kind of think of it as just an effect of Earth's gravity. So uh, so there are different puzzles. The underlying concept of it is each puzzle has a different core knowledge that's required to solve it, and that's typically what the benchmark expects. So it's never just math. It's mostly always just input output pairs of puzzles in this format.
Cool, thank you.
Yep.
Yeah, that's right. The examples are all visual, so there's no text or numeric input. Any other questions?
To what extent are these examples? I mean, just a person looking at them, how would you tell what the intended solution is, I guess?
Yeah, that's actually not a very straightforward, right? I mean, I would just, I mean, again, this is more of like an IQ test, right? I mean, for me personally, looking at this, I see that, okay, in this example one, we have these kind of blue L-shaped kind of grid over here, and then he kind of fills in the remaining kind of block in the square, kind of a filling with a dark blue color. And the same thing happens in example two as well. So I can kind of intuitively say that in the test input output pair, all I would need to do is fill the empty L-shaped black box with the dark blue box. And obviously, this is very specific to this example. In We would have a different knowledge, kind of a core knowledge. So here, the core knowledge is filling. We would have some sort of a different core knowledge for any other different problem. But it's to kind of understand or kind of syntactically mention how is it that I can solve this problem is actually not easy. But I would say personally, this is how I would solve it. But it's typically not really straightforward. It's very intuitive. It's hard to put in words sometimes for different problems. For this, it was quite intuitive.
Yeah, if you don't mind me adding a comment, when I look at the example on the upper left, you see two light blue L shapes. I don't know what to call them, and then two dark blue squares got added. So the rule could just be add a dark blue square that's whatever 2 down and 3 over, and add a dark blue square that's whatever it is 4 down and however many over, right? But then when you look at the second training example in the lower left, it's like, oh wait, the dark blue squares were not in the same location, so it's not necessarily physical XY coordinates. So maybe it's always add 2 dark blue squares, but then when you look, you're like, oh wait, but this one added 3 dark blue squares. So when I think about it, there are potentially multiple valid explanations. I could probably come up with some like 10th degree polynomial that happens to just fit those 2 XY coordinates and those 3 XY coordinates. But I would say the simpler, I don't know how else to say it, but simpler explanation is anytime you see a 3 square light blue L, add a dark blue square in the missing corner to turn it into a 2 by 2 square, right? So it is possible that you might come up with an alternate explanation that you would argue is equally simple, and it's possible that we might not agree 100% on what the correct answers are for all these problems. But I mean, the ones that I've seen, like, yeah, I can't come up with a better simple explanation than just add a 4th square anytime you see those 3, right? So for me, it's a simplicity bias, which, right or wrong, I think is probably a good bias. And if nothing else, that you could learn from the training set that there is a simplicity bias. Not what exactly the rule is, but that you're looking for a simpler rule. Right. So it's like, if I said continue the sequence 2, 4, 6, 8, you probably would come up with 10. And I'm sure there's like many other, like I said, a 10th degree polynomial. We're like, yeah, the correct answer is 5,096, but most of us would say that just, 2, 4, 6, 8, 10 is the simpler rule.
That's an interesting example, the 2, 4, 6, 8, 10 one, because I remember a video done by I think it was Veritasium at one point, that he gave people a sequence of numbers. It was 2, 4, 8, 16, 32, and then asked them what the next number was. And people generally would go ahead and say 64 because it's to the power of n. But his rule was just that the number needed to be larger than the previous one. So, I mean, it's kind of like trying to, I guess that's kind of an example of how people would find that higher order not exactly simple.
Yeah, I've heard people comment about like, is there a certain bias of the people who created the test set, and if you bake those in, so yeah, we can kind of talk about it, but I think going back to the talk, I think clearly you can see this is not something that's just a skill-based thing, like learn long addition, learn long multiplication. We can debate about whether there are cognitive biases, but we're now in a very different domain than just if we were talking about, hey, multiply these 2 long numbers like we saw on the first slide. All right, thanks, Adarsh. Back to you.
Oh. Yeah, those are valid points. I think it's important to understand the essence of ARC-AGI. Now, obviously, as you mentioned, Ted, where you kind of fill in these dark blue squares. Now, obviously, that would work for this puzzle, but I think the essence of ARC-AGI comes, the essence comes where you don't really know what you need to do in the actual test set. Like, you can't hard code that before you actually see the test set. So that's essentially the hard part of the benchmark. As to you won't really know beforehand which knowledge prior is really required in order to solve a particular problem. Anyway, moving on. So we have this Kaggle competition launched on the ARC-AGI benchmark, and let's look at the first phase of the different models trying to solve the ARC-AGI benchmark, which is essentially 2019 to 2014, starting from GPT-2. to GPT-4o. And if you see to my graph to the right over here, if you just look at the number of parameters, if you just compare the number of parameters that GPT-2 had compared to GPT-4o, it is almost a 50,000 times scale up of the model. But if you really look at the performance over here, GPT-2 scores almost close to zero. And GPT-4o scored, I think it was close to like 7-8% on the benchmark back like last year. So you can see that even after scaling up these LLMs to many such billions of parameters, the performance of these models on ARC-AGI, they are not really very stellar. They are pretty much a noise range to zero. So this essentially kind of showed that just scaling up your LLMs is not enough to obtain reasoning. Well, there is some trace of reasoning, but it is extremely limited. So this was the case in the offline website, in the ARC-AGI website, where there was a resource budget and these LLMs weren't able to perform really well. Now, obviously, right, the natural question follows is why is it that these LLMs are so bad at the ARC task? I think I covered this a little bit in the previous slides as well, but the main assumption over here is we feel like the knowledge, the core knowledge, as I was explaining, which is learned by LLMs, is either fuzzy. So when I say fuzzy, what I mean is the core knowledge that the LLM learns, we don't really know if the same, think of it like neurons kind of activating in the brain. So we don't really know if the right neurons are activating in order to solve a particular problem for the model, right? And it's either that or the knowledge prior just does not exist at all for a particular task. That's one. And the other one is also the concept that LLMs at the end of the day are token predictors, right? The next token predictors. And the way the next token is generated is through sampling. However, the tasks like ARC and math, for example, these are deterministic. So introducing LLMs, they are inherently stochastic in nature. So unless we have some way of removing the stochasticity either via multiple LLM calls or I don't know, like maybe chain of thought prompting, like kind of asking the LLM again and again on the same prompt and to see how consistent it is to arrive at an answer. Just a single shot prompt of an LLM won't really yield consistent results because LLMs are inherently stochastic samplers. So but for reasoning, you kind of have an iterative process which is very deterministic based on core knowledge. So that's the case in for the basic big LLMs, like state-of-the-art LLMs at the time. And meanwhile, on Kaggle, the winner of the competition was by the user IceCuber. He was able to score 21% on the ARC-AGI dataset. Now, his approach, on the other hand, is completely different from inference on LLMs. What he did was he wrote, think of them as, so what he did was he has written a few Python functions where he kind of hard-coded a few core knowledge concepts. So say in this example, I want to color a particular black kind of a grid to dark blue. There's a code for that. So basically, if you look at the representation of these ARC data set, the way it's like fed to us, so we are given essentially a JSON string where the black essentially say the color of this is black, so this is essentially going to be 0. So we're going to have a bunch of rows and columns where each element of the row and column represents the color of the particular grid. So what he has done is he has coded up a few transformations in Python on the input grid, and so he called them as primitives. So he had coded out multiple such primitives. So it could be coloring, it could be rotation of these particular objects, it could be counting how many objects are present. Say in this example, let's say in the first example over here, we have two objects, essentially these L-shaped blocks. So he has coded out this concept of counting, and so on. Basically, just multiple transformations of the input grid. He has coded out 142 such primitives, and the collection of these primitives are in ARC terminology called as a DSL, or a domain-specific language. So think of it as a vocabulary to solve a particular, or to solve ARC tasks in general. And what he has done is after coding out these primitives, he has performed a greedy stacking of these primitives. And what that means is, say I have a task where if I color all the objects to red and then rotate them by 90 degrees, I achieve the answer, right? And so what he would do then is he would have the first layer of all 142 primitives, and then he is going to then kind of select one primitive, and then he's going to again kind of call one of the 142 primitives, and he's going to do this on a for loop on different levels, and he's just going to mix and match different primitives, and he's going to check whether we arrive at the answer or not. So it's just essentially brute force search on the primitives. Yeah, that's on the ice cuber approach. Any questions on this? Because this might be a bit of it might be a little involved. I'm obviously not covering the entire details of this because that would actually take a lot of time. But this is the basic premise.
Adarsh, I have a question.
Yep.
So I was thinking, if we train, if we dedicate our training on certain types of software, for example, Wolfram Alpha and things like that, which can do fairly advanced mathematical, computations and stuff like that in area of calculus, advanced calculus, maybe in the area of differential geometry. I'm not quite sure about that. One can go all the way up to that and train the models to leverage that and come up with fairly accurate answers if we dedicate like that. I believe ChatGPT, as far as 4.0 is concerned, it can give a lot of tech information, like it can give code and stuff like that. Whereas for other text processing, they're talking more about models from Anthropic. Similarly, if they're domain specific in this manner, we could possibly come up with really good inferences.
So your question is that if we actually feed in a lot of training examples for a particular domain, that the
Yes.
LLMs are going to do good.
Yeah.
I would say, yeah, you are right. That if given the sufficient number of training examples, the LLM is obviously going to do really well. But the main issue is that in tasks that the LLM has never seen before, right? How would we generate training examples for it, right? Say, for example, the basic, so the reason why ARC-AGI was created in the first place is in order for the LLM to adapt to novelty, right? So obviously, we can obviously feed the LLMs with more and more ARC examples, and eventually they're going to do really well. But we would be missing the point, right? We define intelligence as, at least in the McCarthy school of thought, on which I think Francois Chollet aligns more, and that's why he created the ARC-AGI dataset. But in his school of thought, he defines intelligence as the ability to adapt to novel tasks, right? And if you have novel tasks, you won't really have a lot of training examples for them. And that's the reason why LLMs kind of don't do good in approaches like this. But yeah, that is true. If you are able to provide training examples for every single novel task out there, in theory, the LLM is going to it's going to be AGI, because LLMs are actually really good in sampling from its distribution. So But we know that the world inherently is dynamic in nature, and predicting every single novel situation is nearly impossible. I would say that's my answer to that.
Yeah, I think that's a really good answer, because if you think about something like AlphaFold and predicting protein folding, um, given millions, billions of examples, we know you can throw those into a transformer and eventually it'll learn the pattern. And AlphaFold got very good at predicting protein structure, but it didn't do it, just as Adar said, on novel situations. So uh, if you had a version of AlphaFold that you only gave it 200 examples of proteins and it could predict other protein shape, that would be some form of intelligence. But I would argue that by the time you give it 100 million examples, there's no more novelty. And maybe when it does actually see something novel, that's one of the few times when it's wrong. So that's really what we're testing for, trying to test for here. That's different. Okay. Any other kind of problem like this, we know if you get enough scale, essentially you will have enough examples of everything. So if you have cat and dog pictures, by the time you get to cats and dogs, probably not that hard. I don't know, 100,000 images of cats and dogs, you've probably kind of seen all the different permutations. And so even though you've never seen exactly this cat with this coat coloring, there's no novelty to it.
Well, perhaps they have to start thinking of extrapolation to come up with real intelligence.
Yeah, I mean, this is intentionally an extrapolation task. And Adarsh, I don't remember, what's the size of the training set? It's very small.
Yeah, this I think for ARC-AGI 1, it was around 400 tasks, I think.
Yeah. So
It's
400 of these
yeah.
visual examples is not even remotely enough to really, have a clear pattern.
Thank you.
Yeah.
It's actually a very
behind you.
interesting question.
You have to press and hold it.
Hello. There we go. I have a question. Since the Kaggle test was supposed to be for novel problems, then how did IceCuber determine the 142 primitives? Was there some kind of prior understanding that the problems would include things like recoloring and translation and rotation?
I guess he kind of deducted that from the training examples themselves. So as far as I remember, he kind of like noted it. So I remember, I think in the solution, what he did was he kind of looked at every single training example, and he kind of sees which kind of a core knowledge is really required. And I think all he did was kind of note down the most frequently occurring primitives in his case, and kind of perform a greedy stacking on that. But obviously, there's a pro and con of this, right? Because if you introduce too many primitives in your DSL, your primitives is going to become more of a scale. It's basically like a scaling issue, right? Say I have 1,000 primitives. The depth at which I can search my primitives is going to be restricted because there are more primitives to search for now, and that would essentially lead to the LLMs not really covering the entire DSL at all. So there's kind of a trade-off here. But as for your question, I think what he probably would have done is he would have looked at most of the training examples and probably would have seen what are the most common knowledge priors required to solve most of the problems.
I see. It seems then in that case, as far as novelty goes, there's still a large amount of human input for this particular solution, because the human IceCuber had to go in and figure out what those primitives were.
You're right. I would say so because, but I think that the novelty in his approach comes from the fact that he has created these deterministic knowledge priors in contrast to the stochastic nature of LLMs. Obviously, he is selecting these primitives in a very brute force search manner, which isn't really ideal, but it's definitely a good first step, I would say.
Right. That makes sense. So then if in another competition, there was another problem that involved an action that wasn't included in those primitives, then his model would just be kind of screwed.
Yeah, you're right. Yeah, I think as I would explain in the next slides, the probably the main pathway to solving our competitions is to kind of develop these primitives on the fly, which obviously IceCube's solution is not able to perform. But that would be the ideal case where we can kind of just look at different problems and kind of find these primitives required to solve them.
Right, right.
Yeah, I think that's right. So, from a formal definition, there's no machine learning here because the model never actually learned anything. It was all just handcrafted by IceCubers. So, whether the system is skilled, it didn't learn squat. So, that's not the goal of the AGI challenge. That's not taking anything away from him because we might learn things from how it was approached, but it's clearly not what we're looking for.
Yeah, I think even in his solution, he kind of admitted that his work actually does not go towards AGI, which is actually not true. Kind of deviating away from just the LLM approaches is, I think, a very big step forward because of, as I mentioned, deterministic knowledge bias. So that's actually pretty significant towards the advancement in this aspect. Okay, maybe moving on. Let's actually look at what's really good and bad about IceCube's approach. But I think from our discussions, I pretty much covered everything. So obviously, one good thing is, as I mentioned earlier, we have deterministic knowledge priors to solve problems. There's no more stochasticity involved here. And the more important thing is this is extremely sample efficient, where I don't really need to cram in hundreds and millions of examples for it to just understand one particular ARC task. I actually don't even, in theory, don't even need a single example. All I need is an input pair, and I will just perform. Maybe I would need one input pair in order to validate my solution, an input output pair. So what I would do is I just kind of stack these parameters one over the other and just check if that's essentially leading to my solution or not. So it is in that regard extremely sample efficient, unlike LLMs. So that's the good side of it. The bad side of it is that obviously, right, it is not scalable. As your tasks become more and more complex, you need more and more primitives in your DSL, and performing greedy search on them would no longer become feasible. And there's obviously, as you mentioned earlier, there's no guarantee that the knowledge priors that we have coded through primitives are actually sufficient in order to solve a particular problem. So there's essentially no synthesis of programs. It's all static primitives from the start. I think I covered this as well from the discussion, so I think we can move on. Okay, so we saw until 2024 these LLMs weren't able to scale properly, and IceCube was able to win the competition just by brute force search, and that's all fine. And again, in June 2024, ARC-Price 2024 was launched. Again, it's the same story. We have ARC-AGI dataset, Kaggle competition. We had another one on the website as well. However, this time, by the end of the competition, the frontier models were able to reach very close to 100%. I think O3 High was scoring, which is actually not released publicly, but it was scoring about 85%. And the real breakthrough came from a technique called as test time training. So think of test time training. So this is obviously these are LLMs, right? So this is unlike what we discussed earlier. And I think this was also one of the questions where we were kind of saying that we will just cram in millions of rows of data for every single ARC task, and we'll finally achieve good performance. And yeah, that's true. And that's evident from here that the LLMs are able to do this. And on Kaggle, the highest score was 54% by the architects team. And what they did was, I think they used Nemo. I don't remember the name of the model, but it was an 8 billion model. And what they did was, given the 400 ARC training tasks, they performed, first of all, they performed augmentations of the data. Say in this example, right? I have these blue and dark blue squares. what they did was they kind of say I have an augmentation of coloring where instead of these light blue objects, I make them either red or green and so on. And I just kind of explode my training data. And in that sense, right, I would have many more examples on which I can fine tune my LLM. So the way it goes is I have some static weights before training, and I fine tune my LLM on these thousands of augmented data per training example. I'm going to fine tune on it, and then I'm going to infer on that one particular test input output pair. And I'm going to reset my weights back to the pre-trained weights, and I'm going to train it again for the second task. And I think that's what the architects have done. So this is essentially the novelty that was observed in the 2024 competition. The idea of having these models kind of learn on the fly on every single task via data augmentation. And since there were only 400 tasks, this was actually feasible to do. That's on, I think, test time adaptation. Any questions on this, on active inference or test time adaptation? It's essentially what we discussed previously on the question where we'll just train the LLMs on hundreds and thousands of data per training example. Okay, if no questions, I'll move on. So if you so obviously, right, if you look at what's good about this, it kind of bypasses this inefficiency of LLMs we had previously via data augmentation. Now we actually do have a lot of training data for each training example, and we can actually sample from LLMs in order to have good performance. And do we do actually in this manner do observe some form of fluid intelligence? Because again, right, we define intelligence as the adaptation of the models to novelty. And although we have done it in a way where we kind of bypass the limitation of LLMs, nevertheless, the LLM has never seen this training example before. It has never seen this example before, and the model is indeed able to solve the problem. So it is some level of fluid intelligence. Now, obviously, one of the drawbacks of this is you would really need the correct data augmentations in order to retain the distribution quality of your training set. Because, say, in this example, the objective is to fill the empty black block with the dark blue block. And if I also augment this dark blue to say something like red, the essence or the essence of the problem is lost, right? Because you would no longer be able to solve it. It would be incorrect, the augmentation. So that's but I think the way they have kind of bypassed this is they argue that given that there are so many data augmentations, on average, it kind of worked out for them, and on average, they were able to retain most of the distribution such that the LLM, when trained on, is actually performing decent. And also in the second point, we do see that, as I mentioned earlier, that this is just an engineering patch that we have, and it doesn't really address the underlying limitation of LLMs. Yeah, so that's on the second competition, and now we have the phase 3, which is currently ongoing. It started in March of 2025, and I think it ends in sometime around November. And this time, however, I think Francois Chollet observed that these LLMs are kind of saturating on the ARC-AGI benchmark, and also he noticed that the ARC-AGI benchmark is easily brute forceable. So in order to kind of address this limitation, he has created ARC-AGI 2. The concept is essentially the same, but the tasks are a little more sophisticated. So if you look at the example over here, right, you kind of see that the way we solve the task over here is we kind of color the blocks based on the number of holes it has. Say, for example, over here on the top right corner, he's coloring the blocks as yellow because they have no holes. If there's one hole, he's coloring them as green. If it's two, it's blue. If it's three, it's red, and so on. So that's essentially the core knowledge. It's essentially on identifying the number of holes that are present in these so-called objects and color them accordingly. So you can see that these tasks are a little more sophisticated. And if you look at the LLM's performance on these tasks, we can see it over here. So the base LLMs like GPT 4.5, Claude 3.7, Gemini 2, they basically perform zero. And even the LLMs which were used to be state of the art, like O3 Mini and DeepSeek R1 and the Claude Thinking Mode, even with single chain of thought, they score within a noise range of zero. And if we use the architect approach, which is the winner of the 2024 competition, it scored about 3.5%. And the O3 low model, which was scoring almost 85% previously, is now scoring about 4 to 5%. So I think Francois Chollet was also mentioning that while ARC-AGI 1 was a test for deep learning models, the ARC-AGI 2 is more of a test for this concept of test time training and to essentially challenge how good these models essentially do on test time training. Yeah, that's actually pretty much it. There's also, I think, one more thing I can probably cover is we have ARC-AGI 3 coming up in March of 2026, where the tasks are supposedly more dynamic. I think it's going to be more like an AI agent playing a game. And the feedback, we essentially have no instructions about the environment at all. The instructions are kind of learned through trial and error. And the model essentially interacts with the environment and gets feedback on the game accordingly. So yeah, that's coming up early next year. So excited to see that. But yeah, that's pretty much it on my end. Are there any more questions?
Any last questions?
Can you go back a couple of slides to the again, one more. So I didn't completely understand the concept behind the test time adaptation. You said something about how they were able to create, they were able to perform these modifications to the training data and use that to augment the data set. How exactly did that work? Because it doesn't seem like going back to the ARC-AGI data example. Would the model make proposals for new types of for new potential examples and see if that would work against the test data? I'm not understanding how they were able to produce additional new training data with these augmentations and have that be effective in the test.
So the augmentations which
Yeah, I just want to make sure you understood the question.
Yeah, I did. So essentially the question is I think basically just an explanation on how these data augmentations really work in helping boost the score of LLMs where previously they did extremely poorly.
So I think Adarsh, if you just give some examples, the idea here is that we're applying the same augmentation to the before and the after, and we're hoping that it's invariant to the solution. So if you change light blue to light pink, then we're hoping that the solution is still valid.
Okay. And so for each, what was each test in the benchmark? like this, where it would be given like 3 examples and then basically asked to try and find a rule for that specific answer, and then an entirely different problem was given. It was given different set.
No. So, for example, for just this one problem, if you just rotated both the input and the output 90 degrees, for most AGI problems, you were assuming that the answer is still correct.
Okay.
Okay. So if you can, so again, you're still reverse engineering the test creator's biases, that a rotation would still be a valid answer. Okay. And so if you come up with enough augmentations, rotations, mirror images, change the colors, do all of these things, and if you're right that the pairs are still
They still follow that
following the same rule, how do you get from left to right? Then now, at least instead of having one input example, now you have thousands.
Okay. And
yeah.
So one of the things about this challenge is actually they give you a few examples of something and then they give you a test example. So even on the test set, they're saying like, here's the pattern one time, here's the pattern a second time, here's the pattern a third time, for example. And so the way people have kind of the test time adaptation specifically. So we have 400 training examples truly from the training set, and then the test examples, they give us 3 examples of this pattern, do a bunch of augmentations on that, train specifically on all of the augmentations of that, and then say, okay, now with this one brand new one, what do we predict the pattern is given what we learned from all of our different augmentations of the test examples that we got.
Okay.
Yeah.
Any other questions?
You see, Ravi
one
has
last question here
yes.
in the room.
Yep.
Yeah. Sorry. Just to clarify that I understand this correctly. Like when you run inference on the test set, you basically take your like one sample, you augment it, so you get like 1,000. This one example you want to predict. You train your network with fresh weights on that new 1,000 samples. Try to predict that one sample in the test set, and then for the next test sample, you do the same thing over again. So you train basically during your like inference. Is that how it works?
Yeah, spot on.
All right, thank you.
Yeah, that's right. So you're throwing away whatever training you do after each problem. Awesome. Well, this was great, Adarsh, and as you can see, you got a lot of questions. You had really good engagement. So if there's interest, I think ARC-AGI is ongoing, and as he mentioned, we're now on ARC-AGI Benchmark 2 and ARC-AGI 3. There's a preview online, and it's coming out. So this is a topic that we can definitely follow up on multiple levels in terms of the benchmark itself and the Kaggle competition, the open competition, lots of different topics. So thanks, Adarsh. This was really great.
Yeah, thank you, guys.
All right. So once again, I'm going to make a plug. If you'd like to do a presentation, it'd be great. It could be something like this. It could also just be a problem that you're working on either at work or individually, and you wanted to share some challenge you overcame, something that that you learned. And again, does not need to be like ML news. It could just be like, I had never used, a support vector machine before, and here's something I learned when I was actually using it. All right, so we're going to switch speakers now. Ryan's going to go next with the monthly ML news, and I'll flip this so we can see Ryan on the Zoom. That's not good. All right, well, we'll see if we can get the AV working.
while Ted's getting the video fixed, this is an interesting little leaderboard. So this is their website, and you can see all of the different methods over time and looking at all of the different like top LLMs. How does it fare in comparison to humans and stuff like that? It's pretty interesting that Grok 4 is at the top. But you can see all of the historical methods. So like he was mentioning the architects and IceCuber. So those are the top ones that came out of the Kaggle competitions, but then a lot of them are like the proprietary, like closed sourced ones. So we good on the video now? Okay. Still recording, I think. Okay, perfect. Yeah, so we've started this habit of going through the ML news once a month. So I gathered a whole bunch of stuff from Twitter and LinkedIn and wherever else, and I'll just be running through really quickly some of the stuff that's happened in the past month in terms of AI ML stuff. So one of the cool things that came out is A16Z put out this list of the 100 top Gen AI apps. So everyone's been making these cool, like generate an image, do code, all of that stuff. So A16Z is this VC group that does a bunch of investing in these groups. So they've done a ton of research on what the top things are in terms of monthly visitors and monthly users. So they posted these lists, and you can see what the top things are. So if you look at the top ones, it's not that surprising. It's ChatGPT and Gemini and DeepSeek and Grok. But then if you go deeper in the list, you start seeing ones that you might not know about and might be interesting. So if anyone wants to spend a day, you can go just play with all of the hottest toys, basically. So I've got another section that's just all of the models that have been released. So GPT-5 was a big deal. They released this big model. I think the reception was a little bit lukewarm at first because it was not entirely understood exactly what it was doing. I think people expected it to just like break every expectation, and it ended up just being another march in the direction of smarter. So right before that, they also released the GPT OSS. So GPT-5 was their big Halo closed source option. GPT OSS was them saying, we're going to give you this open source model. Everyone play with our tools. Everyone go deploy it. So they posted it on Hugging Face, and it's a very good model. They have a 20B model and a 120B. So if you're one of the GPU poors, you can still play with those models and get some impressive performance. Along the open source lines, Qwen 3 Max also came out. So this is like a huge model. So the ones we just talked about, 20B, 120B, this is 1 trillion. So very hard to run. Most people probably aren't going to be able to touch this, but it gives very good performance. So it's even beating DeepSeek and all of these other models. So exciting if you have a whole server farm of your own. One of the hottest things lately has been Nano Banana. So this is Google making a image editing, a text to image model. And so this is super cool. You can basically start with an image and say, modify it in this way. And it's become very good at doing these kinds of tasks, saying, put it in this style, or put this person in this position, or have them interacting with something in a certain way. So people have been having a lot of fun with this Nano Banana model. If you want to access that, that's just directly in the Gemini chat interface. Another one that came out that's cool from Google is Genie 3. And so this is their frontier world model. And so in the past month, they released their VO3, and that was their video foundation model. And that's basically like you can generate video from a prompt or from some starting frames. Genie 3 is different in that it's very interactive. So like if you look over here, they have like your keyboard controls. And so you can basically say, generate me this world, and then you just go control inside of that world. It's very interesting to be able to just like play whatever's generated like it's a video game. So you can see in these examples they've got their little robot character and they're able to just look around and then also move through the world, and it's just generating it on the fly. It's just making a video as you're interacting. So like here you can see they're moving the camera around, they're saying go forward, and this is all just on the fly generated video. Very cool to play with. It's not publicly available yet, so you can't really use it, but they claim that it's good. um, in the actual real front, so Tencent has released something that's kind of similar. It's called Voyager, and so this is a Chinese model that can do similar things. You can basically say turn this image or write a prompt and generate some 3D world basically, and then you can go explore within it. So very similar, not quite as advanced. The Genie one is very, very cool, and this one's a little bit more limited, but this is something that you can actually run and play with. Yeah. So the Genie one is just outputting video frames. So there's no actual like objects backing it. And they've made it in such a way that it has good consistency. So like one of the problems with the earlier models was like you turn left, you turn back right, and everything you looked at was just gone. And so this Tencent one is actually creating 3D objects for you to explore and play with. So this is supposed to have good consistency because it's actually generated the things. It's not just making video. So on the video generation front, there's been a lot of cool examples. The VO3 model got better. A lot of the other models have gotten better, and so people have been figuring out how do you make like a full video out of this, because a lot of the tools are limited to make a 5-second video or make an 8-second video. And so people have been getting better and better at using these tools in order to make like animations and little commercials and try on this try on these glasses and make a video of me looking around with my head like that. And so people have gotten very good at this. The models have gotten better, but they've also been building tooling around like how do you make something like this. So 2 new interesting models that have just popped up within the past day or two. I don't remember when, yesterday. So Open Router is this place where you can host all of these different models, and then you can just swap between them, just saying like this model name, that model name. And so Open Router has become this sort of hub for some of the top labs to test their models. So this is where they kind of beta test them. So these 2 models have popped up: Sonoma Dusk Alpha, Sonoma Sky Alpha. And the thing that people are extremely impressed by is they have a 2 million context. So like right now, the best is Gemini with 1 million. So for someone to push past that is very impressive. And so a lot of people are speculating, is this another model from Google? Is it from Grok? Is it from somewhere else? So something around the corner eventually that'll probably be fully released. On the NVIDIA side, CUDA 13 dropped. Probably not that interesting to most people, but they're getting ramped up for the newest GPUs that are coming out. So they release a new version of CUDA, and then it can drive the Blackwell GPUs that will come out eventually. One of the things that got a lot of buzz in the past few days was NVIDIA posted a blog basically saying like, hey, actually, you can do really well at agentic stuff without these massive models. So their idea is you use a massive model to kind of orchestrate things, and then you use the smaller models to do a bunch of your smaller tasks along the way. So you don't have to pay the 1 trillion parameter model to do all of these more basic tasks. So a lot of people have been digging into this and understanding, okay, how do we get this level of performance out of smaller models? because it becomes very, very expensive to run when you're doing everything with whatever the Halo model is. So one of the other things NVIDIA was doing was they're ramping up to release these new GPUs, and they're doing test runs of this new data type. So one of the biggest innovations in recent years has been, first we were doing full precision, and then half precision, and then FP8, and all of this has helped us train bigger and bigger models because it makes them need to do less math and be able to do everything much more quickly, takes less memory. And so they did these massive test runs with NV FP4, which is their new data type. They're saying this is just as stable as FP16, but we can do it way faster because we're pushing less bits, basically. Some of the people on Twitter were laughing because this is their test run. They're doing a several billion parameter model, and they're training it for 10 trillion tokens or something like that. And it's like, you don't need 10 trillion tokens to prove that it's stable. A lot of people would love to be able to train on 1 trillion tokens. So NVIDIA being rich, and the people that that make the GPUs, they can just run them as long as you want. One of the cool resources that I found was from Modal. They have this guy who's just really deep in the CUDA details, and he was basically like, it's extremely hard to break into these things because the documentation is broken across a million different resources, and you have to go read the like CUDA 13 docs that I linked and go all the way back to the beginning to understand what everything is. And he basically created this cool website with an interesting theme that tries to walk you through all of the details of the hardware. So if anyone wants to nerd out and learn some more about GPUs and the software that runs them, this is probably a good place to start. So on the business side, one of the cool AI browsers got bought up by Atlassian, which is, we'll see what happens. Atlassian typically kind of makes enterprise software that's very boring, so they might just kill this browser, but we'll see what happens. This for a while has been like the sexy browser alternative. It's the trendy thing that a lot of people have been trying out as a alternative for Chrome. Multiple things about Anthropic. So Anthropic raised a big, huge round. So now they're valued at this astronomical amount. So they got another 13 billion. One of the other things that happened with them is they got sued for a huge amount because they were using a bunch of pirated books. One of the interesting things that has come out of that is the ruling basically says that they can use the books as long as they physically buy them. So they've now bought millions of books, and they're just ripping them up and scanning them because that is the legal workaround instead of just downloading them. So now they're buying books in mass and then just destroying them, which I don't necessarily think is the better option, but that is the legal requirement now. They need to physically buy them. I think they would. It's just about physically purchasing them. Like if it was on Amazon and they bought it, that's totally fine. But yeah. So other Anthropic news, a little bit controversial. They have put much stronger restrictions on a bunch of different people. So mostly China, but they're basically saying China's a threat. They shouldn't have access to our models, and so they put stronger restrictions on that. And then the other thing was they also cut off access to OpenAI, and OpenAI was very mad about that. So, couple interesting essays and stuff that came out. So there's this guy Ethan Molek, who writes a lot, and he's on top of all of the latest stuff. So he has cool articles. He wrote this one on mass intelligence, and it's just basically talking about how we have access to so much intelligence now. Everyone has this supercomputer access on their phone that can solve problems for them. What does it mean when everyone has access to this? This is very widespread. We're still kind of cresting, like people are just getting access to GPT-5 and other similar models. So what does it mean when everyone has access to this? One of the great lecture series is the CS 231N. So this is natural language processing, and it's a very good, or this is the computer vision one actually. But the Stanford courses have been like very, very important for a lot of people in starting their journey. So it's very high quality. It's all of the top researchers coming in and saying basically like, this is the thing I'm excited about. This is the cutting edge technique. This is the best way to do certain things right now. It just came out a few days ago. So if you're interested in that, that's a very good course to follow along with. So I found this post that is just kind of talking about how vibe coding has been going for one of the top people. He's been at many different companies. He's done a lot of significant work, and he basically said, I've been using vibe coding a lot. Here's my conclusion after using it for a while. Very in line with my experience so far. He basically talks about like it leads to a lot of bloat. So you use these AI coding agents and it's able to spit out 1,000 lines of code for you, but you don't know if that's exactly the code that you want, or maybe there's a more simple way to do it. Like the thing that I felt is for an LLM, it can spit out 1,000 lines of code and that's no cost to it. Whereas for me, I try to do it in the minimum number of lines of code because it takes me a while to actually physically type that out. So for data sets, this new Fine Vision data set came out. And so one of the big things with these LLM training data sets is we have like unlimited text, but people haven't done that much effort on the vision side. So get a bunch of images, annotate what's inside of them, figure out how do we build a good high quality data set. So this is from Hugging Face. So they go in great detail about all of the stuff that they do for gathering the data, filtering the data, all kinds of stuff like that, and then what its impact is on the downstream models. So very cool to have a big vision data set like that. Robotics side, we have a whole bunch of stuff. So this is the Mars personal AI robot, and it's this cute little guy that has a little arm, and you can tell it to do different tasks, and then it will try to go do those tasks. And so they tried to make it simple enough that you can just prompt it. So one of the complicated things with the robotic stuff is a lot of the difficulty is going from like maybe it knows what you're trying to do, but then it has to turn that into moving all of the specific motors and actuators and everything to do the specific task. So this is a fun little thing that pre-orders are opening soon. Figure is a company that I've been following a lot. They have these really sleek looking robots, and they've been showing off them doing a bunch of different tasks. They had a demo with OpenAI a while ago doing similar things. So very fancy robot. One of the cool things that just happened, I didn't know about this until I saw it on Twitter. Apparently there was a World Humanoid Robotics Olympics, and so they have these robots doing all kinds of different tasks. So they had them do dances, they had them do like 400-meter runs and all kinds of stuff like that. So one of the interesting things was in last month I showed off the Unitree robot that was only 16K. That exact robot ended up winning the overall thing. So they did it Olympic style, saying like, here's 20 different events, and then you want a general robot that can do well in all of them. So that Unitree G1 that's only like 16K ended up being kind of the state of the art for that set of tasks. So the G1 was that 16K robot. This R1 is their newer one that's even cheaper. So this one is only 6K. So this is kind of crazy that you can get a toy like this for so cheap. I'm sure it's difficult to program it to make it do things, but pretty impressive that we've got the cost of something like that down so far. Last month, I did a section on just like the top models that are on Hugging Face right now. So I went through and I just went through the Hugging Face page, the trending tab, and then I'll show you some of the models that are on there. So interestingly, one of the top models this month was this machine translation model. So they basically said right now, these LLMs, ChatGPT 5 and everything are great at translation, but maybe we don't need such a big model just to do translation. So this 7B model is maybe 100 orders of magnitude smaller, and it is doing very, very well at machine translation. And so I think a lot of people have picked up on that and started using it. The Voyager model that I showed earlier, there's this vibe voice. This is similar to one of the previous ones we looked at. It's essentially saying we can do text to speech, but we can have very expressive output. So you can tell it, say it like you're scared, say it like you're angry, and it can actually be expressive like that. It's not limited to just the basic robotic voice. I'm not sure exactly my Tuan. This model has popped up and been popular in the past few days. It's a very big model, and people have been joking about it because it's essentially coming from a company that is more like Grubhub or Uber Eats or something like that. They're mostly known for being a food delivery service, and people are kind of questioning like, okay, why does this company need a 500 billion parameter model? So Google released their embedding Gemma. So this is a tiny little model, and it's just focused on embedding text. So you give it some text, it makes some embedding, and then you can do retrieval on that. You can say this article is similar to that article or something like that. They've done a good job training that and just loaded a whole bunch of things in there. This Swiss group has made this Apertus model. And this has been a big effort to make something that is like fully open source. So they open source their training code and their weights and the data and everything, and they tried to make it as compliant as possible. So a lot of the other models, like the Anthropic one, they just say, oh, we'll just download all the books and we'll use them even though we don't have the legal rights. This group has intentionally said like, okay, what can we actually do, trying to work within the rules as closely as possible. So I showed the Nano Banana. Quen released their kind of competitor model. This is Quen Edit, so it's similar. You can give it some image and then say modify it in some way, and then it will do similar edits. Step Fun. This is a audio processing model, so it's the opposite. The other one, you type some text and then you get some voice back. This is saying process the voice and turn it back into text, and also analyze it in various different ways. So some people might take the approach of saying just turn this and transcribe it to text and then ask a question, but the problem with that is then you lose all of the emotion and other non-text stuff. So this one, the intention is basically encode the audio and then directly answer questions from that so that it can hear the tone, it can hear the other non-text things that are happening within the audio. So the GPT OSS showed up top. Not very surprising. So similar theme from last time. So there's one of these models, and it's basically a porn model. That's all you can say about it. But it's interesting that these things just consistently show up in the top 10 or 20 models. A lot of people are using them. ByteDance released another one of these models, and the intention behind this is that there's a difficulty between style transfer and character consistency. So a lot of people were playing with the Google models and saying, okay, turn this into a Studio Ghibli style animation. But that's kind of at odds with like keeping the characteristics of the person. And so this one, they tried to separate the two things and basically say, keep this person looking exactly how they are, but also be able to style transfer them. So they think that they've improved upon that with this USO model. So this is an interesting I assumed it's French. I'm not sure if it's French. But this is an interesting model. And they basically said, everyone else is throwing all of this compute at it. How can we actually pare this down to be as efficient a training process as possible? So we only do 130 million parameters. We do the most filtered data set that we possibly can. We try to pick the best optimizer. We try to pick the best tokenizer. We do all of this stuff and say like, how can we make this the most efficient training process as possible? So we get whatever performance metric. So I was kind of surprised when they were showing this performance chart, like actually it's getting smoked in pretty much every category, but that's because they weren't trying to say what's the most performance we can get out of a 130M. It's like where on the efficiency curve can we get the maximum point for like least amount of training, but best performance. So that's it. That's all the news for the month.
Thanks, Ryan. I always really look forward to your updates. All right, so we are at time, so we're going to go a little bit over. I'm going to make this last part very fast. We had started a computer vision series with two potential sources. One was the Selesky textbook. Once we got into it, found that it really covered a lot of not just machine learning computer vision, but every other aspect of computer vision. So computer graphics, photography, lots of other things. And so wasn't the greatest fit. My plan is to continue reading through that, and I'll bring you guys back nuggets on a monthly basis. The other source is the Practical Computer Vision series, which you can find online. The videos are on YouTube, all the materials in a GitHub repo. And so if I can find that. One sec. All right, let me share my screen. Great. So here we have workshop 4, and this is introducing convolutional neural networks. So for those of you guys who are going through the hands-on machine learning series with us that we're doing most Saturdays, this is going to get introduced in a fair amount of depth in chapter 14. So when we get into the deep learning there, it is going to converge here, but there are some topics that are covered differently here. So at this stage, we've sort of introduced computer vision, and we've seen like how images are stored inside the computer as numbers, as arrays. Are they in certain places, they're integers, floating point numbers. And so today we'll just cover one brief topic, and it's really kind of like this and the next 1 or 2 additional workshops will get us to the point where, again, not really covering the theory, just kind of very going in hands-on. Here are sample notebooks where you can actually play with images, you can actually train some models. And so again, if you If you want to just get your hands dirty, this path is going to get you there really fast. If you're like, well, wait a second, I don't understand what some of these things are. You haven't really explained. You just showed me the sample code and it's running and it works. We will catch up with that in part 2 of the hands-on machine learning book, which is all about deep learning. Okay, so very briefly, the original big success story for deep learning came from computer vision. It was starting 2012 is when we talk about sort of AlexNet, and that was long before LLMs got that good, long before GPT-2 and long before ChatGPT. And the technology that allowed these leaps is using this thing in machine learning that we call convolutions, or I don't know, convolutional layers, different versions of the same word. For any of you who happen to know a lot of math, this is not the exact same thing. This is not the same thing as the term convolution in math. Okay. So briefly, what we have with convolutional filters is the input is a two-dimensional input. Okay, I'm not going to talk about the channels, the color channels too much here, but it has height and width. And what we're going to do is we're going to process that image. And what the convolutional filter does is it says, look at every location in the image, start in the upper left corner, and then for every location, do a certain calculation. All right. And one way to think about it is you do the calculation starting in the left corner, and then you move over slightly to the right, and you repeat the calculation with the pixels that are there. And then you move to the right, and you do the calculation with the pixels that are there. And you keep going. When you get to the far end of the image, then you move down, and then you start back on the left. And so if you're familiar with sort of raster scan, how the old TVs worked, this is basically a raster scan type thing where, again, you're doing a certain calculation. Now, what the heck is this calculation? Well, for example, on this slide, you see a 3x3 matrix. Okay. And so what we're going to do is we're going to take the value of the pixel that's in the center that I'm focused on. I'm going to multiply that by 5. I'm going to take the pixel above it, multiply it by its value by -1. In this case, it's very symmetric. The one below by -1, left, right, -1. And then the corners, I'm just going to zero them out. I'm not going to actually get any contribution from this. Okay. So then I'm going to move, let's say, 1 pixel to the right, and I'm going to repeat this process all over again. So in fact, any one given pixel is going to get used multiple times. It's going to get used when it's the center. It's going to get used when it's the left. It's going to get used when it's the top, right? But you can think of it basically as this small 3x3 local area that you're doing the computation. And so one of the things people talk about is sort of the receptive field. So for 3x3, it's a very close neighborhood. It's just the pixel of interest and the ones that are all around it, either directly adjacent or diagonally adjacent. And every other pixel in the image, you couldn't care less what its values are. You're only doing a calculation. So if you center this filter on every single pixel and you do this process, your output shape is also going to be rectangular like an image. And so oftentimes people think of these as sort of transforming an image based on whatever numbers, whatever pattern you have in here. Let me find, I've got way too many windows open. But this is a PDF, and I wanted to show you something that's a little bit more animated, but I have way too many windows open. Do I have it here? Where do I have it? Sorry, I think it's here. Okay, so this diagram is showing you a very small image. Okay, imagine that on the left here, we have our image, and they're doing the technical work of actually showing you 3 channels. So the top is the red part of the image, the middle is the green, and the bottom is the blue channel for the image. Okay, and then if we have 2 filters in this case, the diagram is a little bit more complicated, but At the moment, the animation now is on the first filter. You can see it's moving and doing the calculation at different locations in the image. For the sake of speed for the animated GIF, if you look closely, you'll notice they're jumping 2 locations at a time instead of just 1 pixel over at a time. All right. And then when it's done calculating everything for this left-hand filter, what it's going to do is it's going to step over to this right-hand filter, and it's going to do the same thing. And if you follow along, then what you'll see is that the calculations it's performing, the output is shown here in the green. Okay. So again, you start with something rectangular or square, and you get something output that's rectangular or square. And these are very local calculations. So for a 3x3 filter, again, it's very local. You're only looking at 9 pixels. If you have a bigger one, if you have a 5x5, it's a slightly bigger area. And if you chose something way big, like a 9x9, then it's actually not so local. You're now looking at kind of a bigger picture. Okay. So what kinds of things? So let me go back to the slides here. So in the past, people, before we had machine learning using these, people figured out there are handcrafted values that you can put in these filter matrices. So this one here is a Gaussian blur, and it might be a little bit hard to tell, but basically the image on the left was the original. The one on the right is the output after you apply this. And what you'll see is that the edges have all gotten softened, so it's just a little bit blurry. Okay. There's also one for vertical edges. This is a black and white image. It's not a color. It's a little bit hard to tell, but basically in this middle one, it's darkest wherever there are vertical edges, so between light and dark. And the one on the right is using the horizontal edge detector. I have a little trouble telling. I can see that the vertical and the horizontal look different. The easiest part for me is this remote control is close to horizontal. And so it has this really dark section right here because there's a pretty good solid horizontal line at the bottom of the remote. Okay, it's not exactly horizontal, but it's close to horizontal. So you can design different filters that will detect certain things like edges and certain patterns and whatnot. And as we keep going through the slides, eventually what we're going to see is that we stop creating these by hand, and now we have neural networks that are trained to learn what sort of values are useful. Okay, but the key concept is understanding that when you hear it's a CNN, it's a convolutional layer, it's one of these small filters. Most common today are these really small ones. It's 3x3. What you do, though, is you stack multiple layers so that you can basically compose things. And so if you had a vertical edge detector and a horizontal edge detector, if you wanted to know if you had an intersection, then you just need to know, is it dark in both of those filters? Okay. Stuff like that. So let me go through briefly. I'm going to kind of whip through these slides. So this mentions that a bigger filter is going to have a larger area. So they show 2 different blurrings with a 3x3 and a 5x5. And then finally, we'll talk a little bit about padding and stride, which are 2 concepts. So if you imagine you have an image and you putting this little 3x3 tiny little checkerboard over it, you'll notice that the number of positions you can put it on is actually slightly less than the width, because otherwise it would be sticking out past the edge. And so there are techniques that you can use to address that. What you could do is you could just fill in zeros. You can fill in black all around the edge of your image. And that then means that if part of this filter is sticking out past the edge, just treat the values as zeros. There's other things you can do where you can repeat values of your image, or you can do a mirror image of it, whatever. But the idea is that there are different forms of padding, and the main reason why people do this is so then that your output is the exact same size as your original input. This works for various reasons within the computer, but I can tell you it just saves so many headaches, because let's say you start with an image that's a really nice power of 2. So it's 256 by 256. If you run it through one of these filters and now it's whatever, 254 by 254, you keep doing this and suddenly you have things that are not necessarily divisible by 2. You get all sorts of problems. So if the output is always the same size as the input, then you at least know, like, oh my goodness, if I start with a nice, multiple of 32, then it's always divisible by 2 and stuff like this. So I don't know if this is really the reason, but for me, it's terribly convenient. Okay. So then we get into, we're going to have the computer learn these images instead of handcrafting them. And obviously we're going to need a lot of training data for it to learn really good stuff. We do run into the same kind of problem that we have even with just linear layers, which is that if you stack a bunch of linear layers, ultimately their expressivity is fairly limited. If you stack a bunch of convolutions, they're still just doing these multiplies and it's fairly limited. So what you do is you add the nonlinearities in between. And so then you can see, here's an example of, we did a convolution, and then we applied a ReLU to it. We did some nonlinearity, and then that tweaks it enough that then if we apply another convolution, it's not just the same thing as if we had used a different convolution that was the combination of the two. All right. Last major topic with convolutions is this idea of downsampling. Okay. If we start with images, typically images are kind of big. They're a little bit unwieldy to use. So 256 by 256 is a pretty small image for, like everyday stuff. I mean, like your phone, what kind of camera does it have on it now? Like a 8-10 megapixel camera or something like that. So it's a lot more pixels than just 256 by 256. So one of the things we can do is we can say that level of detail is not needed to know if it's a dog or if it's a cat. So what we're really trying to do is aggregate things into more global features. And the way we do this in typical CNNs is you start at that detail level, but then you start combining things into higher level representations at more coarse-grained granularity. So a simple thing you can do is you can say, if I start with a 256 by 256, I'm going to have that. And I'm going to have a 128 by 128 representation where every number in that actually represents a small 2 by 2 corner, a small 2 by 2 patch of the original. And then if you have that again, you can get down to 64 by 64. And so eventually you can imagine that if you got down to something like just 4 by 4, 8 by 8 or something, and it had really rich descriptors of what was in, each of those, let's say it's an 8 by 8. So it's like a chessboard, 64 boxes, but it had really rich information about what's in each of those boxes. Then maybe it'd be pretty easy for you to say, does this look like a dog that's looking left? Does this look like a dog that's sitting? Does this look like a cat? But of course, the trick is you need very rich information for each of these spots. So there is this downsampling thing that we do, and there's two ways you can do it. You can do it with the convolutions we talked about, where instead of going one square at a time, if you go 2 squares at a time, then you're going to have half as many outputs. And so that's one way to get an output that's smaller. Another way you can do it, going to the next set of slides, is what we call pooling layers. And so these, instead of using convolutions, just use a different operation. And it's much more explicitly about reducing the dimensionality. So a very simple thing we can do is just say, here I have a very tiny image. Imagine it's only 4 by 4, and I'm going to reduce it to 2 by 2. So I'm going to take this corner, which is the green ones, and I'm going to take the max value. So 0, 29, 15, 100. The max is 100. in the lower left corner, these orange ones, they're all 12. So the answer is 12. That's easy. Down here, 7, 2, 6, 45. The biggest number is 45. All right. On the next slide, you see there's also mean pooling where I can take the average of all of these. Over time, max pooling, you'll see much more often than mean pooling. And the reason is because if you take the average of those pixels, it's sort of like you're blurring together the information from those 4 spots. If what you want is something that acts more like a logic gate that says, do I see a vertical line? Then that's something like max, where just anyone that says yes, then that means I saw a vertical line. And so that's why ultimately you see max pooling more often than these other forms. So a little bit more information in the slides, but for the sake of time, I'm just going to summarize it there. And so we'll build on this next month with the next workshop, the next set of notebooks. If you have questions about either the content, the slides, or the demo notebooks, feel free to ask questions on Slack. But the key two technologies here are these convolutional layers and the pooling layers. When we combine those, what we're able to do is actually build very good feature extractors that will regionally understand what's in the different portions of the image. And then we can kind of combine that regional information to an overall understanding. Do I think this is a dog? Do I think this is a cat? And the key thing about these convolutions is that, one, it turned out that you can do this convolutional operation with a matrix multiply. You don't actually have to go one at a time for each spot. You can do it in parallel in one fell swoop with a matrix multiply. And it turned out that we have these video gaming cards that do a lot of computer graphics, and the computer graphics for speed, they converted everything to matrix multiplies. And so matrix multiply is the main compute workload when you're playing Fortnite or something like that. Okay. And so the ML people in 2012 figured out, I can repurpose this video card for doing my matrix multiplies, and I can do them really fast. And so we have something that then can do these convolutions very fast. And they have this hard-baked inductive bias that says nearby pixels are more important than faraway pixels. And there's pros and cons to that, but generally that ended up working pretty well, because if you're looking at the fur on a dog, the neighboring pixels, what color they are, it tells you a lot about what color you expect this pixel to be. But if you're looking at the eye of the dog or the tongue of the dog, then you're expecting very different values, but it's still true that the neighbors tell you a lot about what you expect to see. And so it turned out that that inductive bias, along with fast compute, allowed us to build these neural networks that could learn well when we stacked layers of these things. We just had to then have a problem that we solved where we would run into things like floating point overflow and underflow when we stacked them. And that's a topic for another day. All right. I know I went super fast. Any questions about the convolutional layers and the pooling layers? Yeah. It, but the idea is that we're applying these convolutions or the pooling across height and width. And what I haven't talked about is we're going to use all the channel information that we have possible. So what we typically do is if you start with a color image, it has 3 channels. It's got more information than grayscale. And then we won't just have one convolution that we run over it. What you'll see is people will say, oh, I ran 100 of those. And we stack up the information from all 100 of those. So the output, if you run convolutions over a 256 by 256 color image, is it starts out 256 by 256 by 3. And the output, if you have 100 of these filters, is actually 256 by 256 by 100. And generally, if you, we'll get to it next time, but if you look at the design of these, what ends up happening is as the image keeps shrinking to a more manageable size, like 8 by 8, the depth keeps growing. And that's because we want enough data to be able to have these rich representations of what's contained in that region. So as it's summarizing more and more of the image, it needs a lot more floating point numbers to carry that representation that says, hey, by the way, I see an ear here. It looks like a dog's ear. And there's also a little bit of this. It's mostly brown, blah, blah, whatever, here's the texture, whatever information it's trying to encode about its little patch that it's most responsible for. That's a great question. Any other questions? Yes. Yep. Yes. So the question has to do with when you're reducing the size, would it maybe be better to do a 3 by 3 versus a 2 by 2? You could do anything you wanted. You could do a 4 by 4. People tried different experiments. The very early CNNs, what you'll see, had larger filters. So there's some 5 by 5s, there's some 7 by 7s. I don't remember exactly the pooling. I think it was mostly in halves, so two-way. But people experimented with different variations of these, and ultimately what they found was, once we conquered the problem that I haven't answered about how do you deal with floating point overflow, underflow, and all these things, and you can build really deep ones without things breaking, they found that doing small increments but having really, really high depth ended up working really well. So AlexNet, VGGNet, these models are like, I don't know, 10 layers deep or something like that. And these days, I consider ResNet 50 small, and ResNet 151 is a medium-sized, decent model. So 151 layers. So then what they do is they almost exclusively use small filters, which means 3 by 3, and they're always typically odd because then like which is the center pixel of interest, right? So 3, 5, 7, right? So they're using the smallest ones, 3 by 3s, and they're using the smallest poolings, 2 by 2s. It's a great question. It's perfectly valid to do any other kind of pooling. It just turned out that doing a little bit at a time, but doing a lot of them worked the best in terms of getting the computer to learn the patterns. Thanks. Any other questions? All right. Thanks for staying the extra time. We'll wrap things up here. So next week, we're back to the hands-on machine learning book, and it will be Hummel chapter 5, I believe, support vector machines. It is going to obviously talk about support vector machines, but as we're also big picture learning about how to formulate ML problems and things like that, there's a little bit of broader discussion around setting up problems training, and a little bit of this idea of classification and like separability of your classes, things like that. Primarily, we'll talk about the actual SVM algorithm, but a little bit of the big picture. And again, we're continuing through this to get a really good understanding of attacking ML problems. Then we'll finish part 1, and somewhere around, I think, chapter 9 is when we begin the deep learning part. And the 3rd edition is still TensorFlow and Keras, but the author is coming out with a new PyTorch version of the book. It's not fully out yet, but we're planning to use the early work so that we can actually cover both PyTorch and TensorFlow. All right. Thanks, everyone. See you next week.